Okay guys, once again very warm welcome to my YouTube channel. Today's topic is about Poiseuille Flow. It is one of the very basic types of flow which is discussed even on the bachelor level in fluid mechanics, and I just thought of doing a simple tutorial how we can compare the analytical results with our CFD simulation. So what actually is Poiseuille flow? It is normally assumed in this flow that if we, example, take this channel or this two-dimensional duct, the two plates at the top and the bottom are fixed, yeah, but the pressure is only varies in the x direction. So if you say that the velocity is in let's say y, your vertical, and the third dimensional, which is the z direction, which is velocity w, is 0, the continuity equation which leads to the conclusion that the overall velocity, which is a function of y. So you can see in this duct, later on I will be modeling with the same approach, that the center of this duct is at y equals to 0, and positive side is like y equals to plus h, and the negative side will be y equals to minus h. So we will, in the next slide, I will be showing you the dimensions of the geometry. So a typical solution within such channel flow is happening due to the pressure gradient. And an analytical solution, or the equation for the velocity, is of such form, and the k here is the pressure gradient. And our aim now for this CFD simulation is to determine the velocity at the center line, which is y equals to 0. And we can see in this figure that you will be having a maximum velocity at the center of this channel. You can see this is both upper and the bottom, let's say the walls are fixed. And this is something which we will be like trying to validate or verify with our simulation approach. So if you take into account y equals to 0, meaning that this value will change. So y equals to 0, so this equation will get reduced to this form. So the problem setup will be like this. We are assuming here a fully developed steady state laminar flow, and it will be a two-dimensional flow, as it is just for the demonstration purposes. So I try to simplify the problem. And the length of the computational domain, which is, let's say, this length is L, it's 6 meters. The width of the channel is y, which is equal to 2 times h. So h is like y equals to plus h, y equals to minus h. So in total it will be like 1.4 meters. So this is the total width of the channel. We are assuming here just a dynamic viscosity of 1 Pascal second, constant of K, just pressure gradients of 1 pascals per minute. And density is, I would say it's, you can say it's irrelevant, because at the moment we are just assuming a constant density. It's a laminar flow, very, very slow. So if we calculate our maximum value, keeping into account all these aforementioned values, we end up getting a maximum velocity at the center of the pipe, which is 0.245 meters per second. And similarly, that leads to a Reynolds number of about 0.343, right? So just take into account that for the velocity, I'll be using the maximum velocity to calculate the Reynolds number. And for the boundary conditions, as already mentioned, I'll be applying no slip boundary condition on the upper and the bottom walls, or the edges of the channel. And since we are assuming it's a fully developed flow, so I'll be imposing a fully developed flow in such a way that we assume periodic boundary conditions on the extremes of the domain, like the inlets and the outlets. So as in a Poiseuille flow, the motion is actually driven by the constant pressure gradient. So this pressure gradient can also be introduced in like a body force into your simulation. You can take it as an analogy, like for example a gravitation, and this term is incorporated by enabling the momentum source option in Star-CCM. So I will also show you later on when I will be demonstrating this. Okay, So let's start now with our live demo. As always, if you have not seen any of my previous Star-CCM Plus videos, so this is always my standard approach. I first of all start with the problem description, tell you about the problem setup, the boundary conditions, and what steps we will be taking on. So I'll be starting with the geometry modeling, we move on to meshing, solver setup, results, and in the end, it will be a summary or conclusion. So let's move on to our demo now. All right, here we are. We are in now Star-CCM. I just named this file as Poiseuille Flow. So we will be starting now with this in the geometry module. First of all, we will be modeling the geometry of this 2D channel. So X dimension will be 6 meters. So this is total 6 meter length. So we start with our y1 is like 0.7, and we can say y2 is minus 0.7. So we'll having in total it will be like 1.4 meters. So if we just open a new geometry scene, so it looks like this is our geometry. And before really proceeding with the other steps, first of all I would like to split the patches so we can define. So if you select this patch, you can call it as an inflow. You can simply use, let's say, this one. So this will be minimum Z. You can name the patches as according to your requirement if you want, but I normally do it like this way. And this is our outlet. That is the top part. These are the wall boundary conditions. So the remaining one is this one. This we will simply rename it here, which is this block surface. So we will call it as bottom. So once you have this done, you have split the whole geometry or this block into several patches, which will be used later on for the boundary conditions and for the meshing to define our regions. So now I will say create mesh operation, as I'll be using a 2D approach. So I will be using now a batch for 2D meshing, this one, and I will say execute the operation upon creation. So this kind of a red circle on the minimum Z plane is indicating that now from there on later I'll be just using this 2D badge. So this will be my 2D plane which I'll be using for meshing. Before really starting with the meshing, I need to give it my part to define it to the regions. So I will assign simply parts to regions. I'm happy with this. Create one region for all the parts. But I would like to define each part surface as a different boundary condition. So there you go. We have our region here. It's already defined. You can see that. So for the inflow and the outlet part, I will simply define it as a velocity inlet because I will assume later on this fully developed and periodic boundary condition. So let's start now with our meshing. So for right click the operations option here, start with automated mesh 2D. So I'll be simply taking quadrilateral measure. I will say OK. And before starting with the meshing, let's make a mesh scene. So this is our quadrilateral measure. For the base size, we stick with 1 meter, and we will say just to reduce it to about 5%. So in order to get a really nice fully structured mesh, I will simply give both the target surface size and the minimum surface size the same percentage based on the base size. And now I will simply press mesh. Once the meshing is done, so it will be updated accordingly. So now if we open a new mesh, so you can see it is looking like this. And if we go here, so now how to improve that, let's go it a little bit with a slow option. Okay, so now we have our surface growth rate which has been done. So this is our mesh. I mean, if you want, you can really go for a much finer mesh, but for as this is just for the demonstration purpose, this tutorial, I think that should be okay. So we will define our continuum now. So right click on the physics, and then simply say it's a steady state model. We will stick to the material as liquid. I will be taking coupled flow. It will be a constant density, and it's a laminar flow, right? And if you remember the slides earlier on, I told you the densities, I'm taking it as 1 because since it is really irrelevant at the moment here, so I will, for such type of flow, I will say it's 1, constant density, so we'll be taking here 1. And then the important step which is now coming is how to turn on this momentum option. Like I was telling you, it's like turning on a gravitational force. So similarly, you can turn it on here. So you go and you will say momentum source option specified. Once you specified this one, so here you will be applying this pressure gradient, which is like 1 here. And another thing you have to do that in order to get this fully developed periodic flow, so you select both these inflow and outlet by pressing the control on the keyboard, control button on the keyboard, and right click and say create interface. So once you create this interface, which is this one, so we will see our type is internal, and we will be saying it is fully developed interface, and I'll be using a periodic boundary condition, right? So I think other than that, there is not much to set it up. Now we will define our scalar scene. So we will be simply plotting here the velocity. So let's say the velocity magnitude. I'll make it a little bit bigger. I'll go to the scene. We would like to have smooth filled, and we would also like to plot the velocity at some specific distance along the x direction. Let's take so it's 0 to 6 meters. Let's take, for example, 5 meters. So it will be a horizontal velocity profile. Let's plot it against the vertical direction. So if we take 0.7 and the other side is minus 0.7, so this is how it looks like, no displayer. And I'll be using this plot, XY plot, to plot the velocity, which will be the horizontal velocity at this particular location. So you need to swap the units. So instead of plotting in the x direction, we will be plotting the velocity. So that will be our velocity in the x direction. That will be the I. And we need to swap the y1 with the direction. So the direction here will be from the vector, we have to change to y. So this is x will be 0. So we'll be taking this one. All right. Now if we initialize our solution, first of all, so we will see as we run the solution, so we will not be changing any stopping criteria. We'll just stick to the default values. So it's like 1000 iteration, which is more than enough to get a converged solution for such type of a flow. So let's start with our simulation. It's done. So you will see as it really runs, it converges very, very nicely, almost to machine accuracy. Yeah, we can see that how it's really behaving, and this is how the flow is looking like. So there is already a good indication that we are getting almost a 0.245 as a maximum velocity, and you can see that since it is assumed it's a fully developed flow by imposing this periodic boundary condition. And you remember that we just plotted at around this position of about 5 meters this velocity profile, which is really looking like very nice and smooth one. Okay, and I'll just show you it's as I mentioned, it's very nicely converged, and you can see the convergence values or the residual is going to about for the velocities x and y momentum about e to the power minus 11, and the continuity is e to the power minus 13. I mean, you can't get a better convergence than that. So which is really awesome. So I would say that we can now say that we have successfully completed the simulation, and if we see that the maximum velocity which is at the center, like y equals to 0, if we really see this value, it's coming to about 0.245. You just do the probing, you take your mouse at this point, it's 0.245, and that is the one which we already have like calculated by using this analytical approach. That means we can see so if we really see this velocity profile, so that's the same profile which I have shown you in Star-CCM. I am exported it in Excel, and just to make it a little bit nice or better, so we can see that the maximum velocity at the center line is about 0.245 meters per second, which really matches very well with the analytical approach. So that means we can say that we have successfully validated this type of Poiseuille flow using Star-CCM plus, and we have shown that or seen that how to set up this kind of laminar flow due to the pressure gradient within the channel flow, within this channel flow type, by using the appropriate boundary conditions, or I would say better to say that set of appropriate boundary conditions. We have used or fixed the plate, two plates on this channel plate, the top and the bottom one, and we have imposed a fully developed flow, steady state, fully developed laminar flow by imposing a periodic boundary conditions. We have already done the necessary post-processing steps. And as mentioned earlier, so I will repeat once again. So the comparing CFD results with an analytical solution um, gives us, uh, I would say, a really great comparison for such case with almost 0% error. So with this, I really conclude the simulation. And before I close this session, I would request once again to subscribe my channel if you have not done it until now, and give thumbs up and turn on the notification button so that you get all the incoming videos. And if you have any requests, anything you want me to do, any kind of simulation related to fluid mechanics or anything else like aerodynamics related to the CFD topics, just write it in the comment section. Thanks a lot. Have a nice day. Take care. Bye bye.